University of Chicago. I'm Director of Research Engineering for the university, primarily for space physics, astrophysics, and we do a little bit for some of the University of Chicago hospitals. I've got a group of engineers that work for me, some based here at Yerkes, others are in Chicago on campus, and we have some at Argonne. So we've got really 3 places, and then we deploy. Usually we send somebody to the South Pole in the South Pole summertime. So that's what we do with our engineers. They are professional engineers. And some of you may not know this, University of Chicago does not have a school of engineering. University of Chicago is a research university. So the nuts and bolts stuff they use leave to other universities. So we're kind of what the university relies on to support where the engineering infrastructure support for the research scientists. A lot of the work that we do is NASA supported, some supported by National Science Foundation, and occasionally we get some NIH or DOE, but most of it's NASA. The project that we have going here at Yerkes today is called HAWC, H-A-W-C, and it's for the NASA Sofia aircraft. And some of you will be familiar with that. That's the 747 with a camera, with a telescope built into the fuselage. And the fuselage opens in flight, 2.5-meter telescope. The camera we are building fits on that telescope, and it is designed to look at wavelengths that are in the infrared. So 100 microns and longer wavelengths are what we're looking at. So you can imagine how difficult it must be to find the infrared light, because it's measured, of course, by the amount of heat that will get to the detector surface. So if we've got a scientist that's studying cosmic background or cosmic dust, how much heat from cosmic dust that are millions of light years away can possibly get to a camera that's buried in the fuselage of a 747? And the answer is practically nothing. How could it possibly be? There is a way, and that is if you get your detector surface cold enough, it can feel the difference. Our detectors operate at 0.2 K, a quarter of a degree above absolute zero. And the engineers here at Yerkes are very good at the cryogenic systems that support that. We've been doing it, this is the 3rd generation that we've done for NASA on airborne astronomy. And this one happens to be a big one. It's a 1,300-pound payload. We've got that instrument in a lab here. Now this group is too big to go into the lab. So what I'm going to do is I'm going to open up the lab. You can kind of go by, you can peek in, you can take a picture if you'd like. And then we'll talk about it when we get down the hallway a little bit. So we're going to do that. I'm going to open up the lab. You can peek in.
So that's colder than the lights.